Alright, what's going on, you guys? Another LeetCode video today. This problem is called word ladder. A transformation sequence from begin word to end word using a dictionary word list is a sequence of words such that every adjacent pair of words differs by a single letter. Okay, begin word does not need to be in word list. So given two words, begin word and end word, and a dictionary, they want us to return the number of words in the shortest transformation sequence from begin word to end word, or 0 if there's no possible sequence. So let's look at examples to see more what this means. Okay, so if begin word is hit and then end word is cog, and we have this word list, okay, a bunch of words that basically are all three letters. All of the words are going to be the same length, right? So, and we can see that. Let's see, where is that? End word length is going to be equal to begin word length. Also, right, word list I dot length is equal to begin word length. So all of the words they're guaranteed to be the same length. Okay, they're also only going to consist of lowercase English letters, right? The begin word and end word are guaranteed to not be the same. Okay, every word is guaranteed to be unique, so there's a lot of guarantees, right, with the constraints that kind of make it a little easier. But nevertheless, let's look at what they're actually looking for. So they're looking for the shortest transformation sequence. So we're starting with hit, right, which is, by the way, not guaranteed to be in the word dictionary, right? However, the end word, the end word is guaranteed to be in the word list, right? But there isn't necessarily a path to that word, right? So, or actually, no, end word is not in word list. So the end word doesn't have to be in the word list either. So it isn't necessarily in there. But yeah, so let's look at this. So hit, right? We're changing the middle letter here, right? So we're going from hit to hot, right? That's in the word list. And then we're choosing dot because we can change the first letter there, right? And that's also dot is in the word list, okay? And then we're gonna choose dog. We're gonna change the T to a G. It's also in the word list. And then finally we can get to cog. So there can be multiple transformation sequences which are the shortest, but this is going to be the shortest. And then they want us to return 5. So just the total number of words in that sequence, including the begin word and the end word. So yeah, let's get into the whiteboarding. So you could do this problem with a depth first search. Actually, you can't. I mean, you could try, but you're gonna get time limit exceeded because basically we're looking for the shortest path, right? So you could try a DFS. The issue with that is, you're searching deeply, unnecessarily, essentially. We're going to want to do a breadth first search basically to minimize the amount of work we're doing, right, in finding that shortest sequence. So let's see how a breadth first search would work. The first thing we're going to do is we're going to put each of these words into a hash set, right? We want to put all of these into a hash set, and the reason is because there's a few ways you can do comparisons to tell if two words are, or there's a few ways you can basically search for the next word that's one letter apart. You could either compare the words, right, which, if you could potentially iterate through every single word in your word list, right, and then just compare each word and see, okay, is this word, are there any words that are off by one letter? But the issue with that is, if we look at the constraints, let's look at the constraints. You could potentially be going through 5,000 words, right? And then comparing, and they could be 10 characters long. So 5,000 times 10,000 in the worst case, pretty much what you're looking at there. That's really big, right? The alternative is we can simply iterate through. We can turn every word in word list. We can put them in a hash set, so we have constant lookup time, and we can just go ahead and replace every character one at a time with every possible character in the English alphabet, and then just do a O of 1 comparison to a hash set, right? So what would the time complexity of that be? So before we had 5,000 times 10, but with this other method, we're gonna actually have 10 times 26, right? And then it's an O of 1 lookup in the hash set. So 10 times 26 is way better than 10 times 5,000. So that's why we're gonna put everything in a hash set. So we're gonna put all these in a hash set, okay? And then we're basically gonna start our BFS with this BN word. So let's build a graph here. So we're gonna have hit, right? Okay, and that's basically gonna be the beginning of our BFS. Okay, so we're gonna basically replace every character in hit one at a time with all 26 lowercase English letters. So we're gonna start with the H, right? We wouldn't find anything, would we? Yeah, there wouldn't be any valid transformations with H. So we would then go to the I, we'd replace it with every letter. And we would see that, this O, that does, we would find that in the hash set, right? We replace the I with the O. We do an O of 1 lookup in our hash set. We'd find hot, right? So that's one way we could go. So let's put that. So for a BFS, and that's a big arrow, probably too big. So, right, so the next, we'd add that basically to the next level in the BFS. Okay, let's keep looking for replacements of the center letter. There's nothing else. Okay, so we go to the last letter, and we keep looking for, we're doing those O of 1 comparisons with each letter, and we don't find anything. So now basically we're gonna go to the next level in our BFS. So we'd be at hot, and we're gonna do the same thing, right? So we're replacing, and also, so I forgot to mention this, once we have basically used a word from our hash set, we can remove it from our hash set, right? Because basically that's gonna be behind us in our BFS. We don't ever wanna look at it again. So we're basically gonna prune words that we've already visited. Okay, so hot now is gonna get removed, okay? Now that we've added it to our BFS, okay, so we're gonna replace the H, and we could see that once we get to D dot, that's a valid next word. So let's put that over there. Let's see. Dot, okay, and that's gonna get removed from our hash set now that it's in our BFS. So we're still on H, right? We're replacing every letter. We're gonna see if there's any other letters, right? Lot is also a valid, next node basically in our graph, right? So we would add that to our BFS, lot, right? So let's add that, and then we of course remove it from our hash set. Okay, and let's see any others. Doesn't look like it. So now we're gonna go to the O, right? And we're checking for replacing the O. There's not gonna be any matches there. And then we check the T. Likewise, there's no matches there. So then we move on in our BFS to these nodes. So let's do dot first, since we added it first. So we'll try to replace the first character. There's not gonna be any matches there. Second character, now you can kind of see why we're removing characters we've already, or words we've already visited, right? Because we'd be doing redundant work. Right, so replacing the first character, we don't get any matches. Second character, no matches. Third character, we are gonna have a match with dog. So let's add that down this path. Okay, so dog, and of course remove that from our hash set. And that would be the only transformation there. So for this word, we've got to do this word also, right? We're going to see log, that's a possible transformation once we get to that last letter there, right? So there's no other options that would work. So we're going to take log and we're going to add that to our BFS this way. Log, right? Okay, and then finally, right, we're gonna do BFS. We're going down to the next level now, so we're gonna do dog and log. But we're gonna see, right, once we get to this first letter in dog, we're gonna see cog is right at that is the next letter in that transformation with the D, right? Replace that D with the C. So let's add that over here. Okay, and then we would try to do this word and there wouldn't be any matches. Okay, and then the next level of the BFS, we're gonna, handle this, and we're gonna be checking right at each point in our BFS, by the way, is this word equal to end word? Cog is now equal to end word, so we can simply return. Also, we were counting, at each level in our BFS, right? So like this would be, and that's how we get the answer, right? We would start with a 1, okay, and then we'd have a 2 here. This is level 3. This is level 4. And this is level 5. So we return a 5 basically once we get to cog. So that's how, basically in a nutshell, how we're going to do this problem. In terms of the time and space complexity analysis, we're going to have a time complexity that's big O of m times L, right? So m is going to be the length of our word list. L is going to be the longest word in our word list, which was, I think, 10, right? What are the constraints? M was 5,000. And then we're going to have a constant here, right? Because we're going to be replacing every character in L with every character in the English alphabet. So technically, this is a constant. I don't know why this is being so buggy, but this is a constant, right? This 26. So like you don't really need to include it there, but just because it's kind of a big, it's kind of computationally expensive, so I'm going to include it here. So big O of m times L times 26 for the time complexity for that breadth for search. The space complexity is going to be, let's see, we have to put all of the words into a hash set. So right there we've got big O of m space. We also are going to have a Q for our BFS, which, technically could, in the worst case, have m elements in it, I guess. But yeah, big O of m, because we're going to need all of these words in a hash set. You could argue it's m times L if you're counting the space for all of the characters too, but at big O of m, it's just all the words in that hash set, that were in that word list. So, and I think, honestly, yeah, I'll go back over the time and space at the end of this just to make sure I'm, not messing up on those. So, okay, so let's get into the code here. So the first order of business is, let's get an unordered set. That's going to give us a hash set with constant lookup time in C++. And it's going to be an unordered set of strings, and we need to basically put all of the words in word list in there. So I'm just going to call this hash set. And basically a quick way we can initialize this is just take the word list dot begin, so the first iterator, and then word list dot end, the last iterator. Okay, and then that's going to quickly initialize that unordered set for us. That's going to be a linear operation, but with respect to the number of elements in word list, but syntactically pretty low code. So we also need a Q for a BFS, right? So just say Q, and it's going to have strings in it, right? And we'll just call that Q. Okay, we need to push the begin word into our queue. So let's just say q.push begin word, and note that the begin word doesn't necessarily have to occur in the word list, but it could. So, and it could, and we can do this penalty free. And by this, I mean erase the word from the hash set. So even if it isn't in there, like we can still do that. C++ will be fine with it. It just won't do anything if it doesn't find it. But we're gonna erase it. We're gonna prune it just in case it's in there. Okay. We also need our to know what level we're at in our BFS. That's the result they're looking for, essentially, right? So just to have code clarity, I'll call that level. We'll just call it level, right? This is the level we're at in their BFS. At first, we're at 1 because they want us to include every word in the transformation sequence, including where we're seeding the BFS. So we're going to instantiate the level is going to be 1 at first, rather than like 0 index levels. It's going to be 1 index levels. Okay, so now we're just going to loop while there's still stuff in our queue, right? Just a simple BFS. So while not queue.empty, and we're going to need to get the top word from our queue. Also, we're going to need to know how many words we're iterating through at this level, right? So that's really the first thing we need to do. So we'll say level size will be equal to the queue dot size, right? And then we can go ahead and loop through, that many levels. So for an I equals 0, I is less than level size, I++, and then we can go ahead and get that word from the front of the queue. So we'll say string word is going to be equal to queue.front, and then we can pop from the queue, so queue.pop. Okay, and at this point, now that we have that word, we probably want to check if it is equal to the word we're searching for. So let's just check that. So if word is equal to end word, then we can go ahead and let's see, return. We can just return the level size, right? Or not the level size, but the level number that we're at, right? So we can just return level. Otherwise, we're going to try and find its neighbors, right? So we need to loop basically through every letter or every character in this word, right? Every letter in this word. So we're going to use an inner for loop with j, and just loop through word.length, and then do j++, okay? And we basically need to replace every character with every character in the English alphabet, right? So, and we need to remember what the character is, right? Because, we're gonna need to basically have that word intact, right? Or not have the word intact, but right, once we go to the next character, like we want to be able to reset the character that was previous. So we'll say char c is going to be equal to, let's see, word j, right? So we're remembering this character, okay? And now we can loop through, we'll say use k, well, k equals 0, and we've got to initialize that data type. So int k equals 0. While k is less than 26, k++, okay? And then we're going to basically just replace word j with the character indexed by k. So we can say, let's see, it's going to be k minus a for basically just to get the character. So, okay, so we have replaced the character. Now we need to check to see if it's in the hash set, right? So, so we'll just say if hash set dot find word does not equal hash set dot end. So if it's in the hash set, this particular, word that is one letter different, if that is in the hash set and it, hasn't already been crossed out, then we can push it into our queue. So we're gonna say queue.push on word, and then we're going to mark it as visited by removing it from our hash set. So hash set dot erase word. Okay, and after that, once we're done with this, trying every possibility for this character, we're gonna set that character back to what it was before and then move on to the next one, right? So that's how we're gonna do that. At every level in our BFS, right, we're going to increment the level we're at, so level plus plus down here. And, if we never get to this line of code, if we never find the N word, what they want us to do? Just return 0 if there's no possible transformation sequence. So if our BFS basically exits without returning level, we can always return 0. Okay, so this is pretty much it for the code. Once again, the time and space complexity is going to be, let's leave a comment. So the time is going to be big O of M times L times 26, right? And then the space complexity is just going to be big O of M. So, or big O of M times L, but big O of M for basically mostly dominated by this data structure right here for the space. So yeah, hopefully this video helps you understand word ladder better. If it does, okay, let's see, we're actually getting a bug, so we're gonna have to fix this. Let's see, so we have our set queue, push, we're popping. Let's see. I have a feeling it's a simple mistake here. K plus A, yes, very simple, right? So for when we're setting the word to a character, right, we actually want to add K to the first lowercase English letter, not subtract it. Subtraction is used when you're indexing into, indices. When you're converting integer to character, you add. When you're converting character to integer, you subtract. So there's a little mistake there. But yeah, hopefully this video, hopefully it helps you understand word ladder better and graphs and breadth for search. If it does, leave a like and subscribe. And I'll see you guys in the next video. Peace.